I'm delighted to be here this afternoon, and indeed, yes, I'll speak about tailored reinforced concrete infrastructure, and particularly it will focus on the CO2 impact of concrete. So we first can consider what the CO2 impact of cement and the manufacture of cement is, and it's responsible for 5 to 7% of global CO2 emissions. I think what great strides have been done in terms of reducing the emissions associated with the processing and manufacturing of cement. But one thing we must keep in mind is that currently the calcination, which is the chemical reaction of transforming limestone into cement, is responsible for about half of the CO2. So that's CO2 we're stuck with, and really the best way to reduce the CO2 emissions is to reduce the amount of cement that we use. The challenges when we move to concrete is that we consider concrete as a bulk material. So we describe concrete as a general term. There's a fragmentation between the structural and concrete mix design in that the structural engineers may have particular performance measures. The concrete technologists are then trying to deliver that, but also considering things like workability and on-site considerations. But there's not necessarily the open dialogue and iteration between the two. There's potentially conflicting requirements throughout the lifetime of a structure, so it might be that we need additional strength for, say, early strike time, but that's not cement actually that we then need throughout the lifetime of the structure. So we need to then think about what is dominating the need for the cement in our structures. But indeed, there's very high consequences if the structure is non-compliant and the concrete does not meet the spec. So that's the context. There are a number of strategies for cement reduction. I've named a few here. The first one is don't use it, and that we've had reiterated a number of times this morning very succinctly about making better use of our structures, reuse, adaptation, durable structures. There's ideas about geometric minimization, so looking at shape optimization, efficient structural design, so if we can minimize our cross-sections, we can reduce the volume of the material used. We then have ideas about material development, so cement replacement, looking at lower cement contents in our materials, and then functions, looking at new functions of our concrete, exploiting our inherent functions like thermal mass, as well as strength, as well as others. So I think there's a piece here which resonates with the themes of this morning, which is durable structures, efficient design, lower cement content, and exploiting inherent functions are things that we are doing or should be doing anyway. And that is really a quick win for us, is to really strive to do the most efficient design and lowest CO2 impact that we can anyway. But then there's the piece, and if I think of the framework from earlier, this is moving from maybe efficiency to more clever design, and that's where our ideas of tailored reinforced concrete come in. And to set this by context, a great advantage of concrete is that we can change the mixes, proportions and constituents such that the ECO2 varies as well. And so the advantage is we can actually look to have lower CO2 mixes. This is some work from one of my PhD students, Ma, and all she's done here is she's looked at published results in the literature whereby people have reported their compressive cube strength as well as the constituent materials. We've used factors then to convert that to the ECO2, and she's plotted the distribution that she gets. Amongst this data, there are mixes that are vibrated concrete as well as self-compacting concrete, and there's a large spread of data, and this is due to constituent materials, construction method, and target properties. Now, important caveat is many of these are research papers, so people were looking to investigate certain parameters, and indeed there may be reasons why a particular performance measure requires a large cement content and hence associated CO2 footprint. But there may also be cases where for our performance requirements we can push these down to the lower end of our ECO2 mixes. And so again, that's a piece that we should all be doing in terms of using best practice in the lowest cement content that we can. But then there's a further piece to say how do we do even better than best practice. And that's what we look at with our tailored concrete. And the idea is to reduce the CO2 content of our products, and that's through using multiple mixes within a single element. And this is also referred to as functionally graded concrete. And so instead of having one bulk mix throughout, we potentially use more than one mix. What we then find is that we can design the materials to meet specific performance requirements, and we only will use high cement content where absolutely necessary. So potentially it's best to do a sort of case study, a thought experiment to think through what this may mean. And so if I look at one where I've looked at a slab on a beam, and the bulk slab I've allocated as a durable concrete with a fairly high cement content over about 600 kilograms per cubic meter, normal density concrete of 2,400. If we then think of a tailored idea where if we only really need that outer concrete to be durable, but we can accept that the inner bulk material has a lower cement content that then is potentially a lightweight concrete, we potentially have that the row of this inner material could be, say, 1,500 and the cement content maybe 300. So if I look at those figures and I use parameters of the thickness of that outer layer, an overall width of B and a height H, and I make some assumptions about this particular section, so I say H equals 2B, the thickness is 30 millimeters, say, and the height is 400 millimeters. If I do a calculation using these numbers, we find that there's about 30% CO2 savings. That's significant if you think that concrete is 5 to 7% of our global emissions. And there's also 25% weight savings. That's also significant because often we're using concrete to hold up other concrete. And so if we have lighter structures, it means the other elements can be smaller and more efficient as well. So I've highlighted here a piece of this structure because it's all well and good to kind of draw these using shapes in PowerPoint, but how would we actually make an element that was something like this? And this is an initial prototype that we've looked at where we have a protective outer layer of concrete with high cement content, and then we have a lightweight core with a lower cement content. So these are two different mixes. We use a lot of colors in our lab to try to differentiate between two mixes. So these are both concretes, it's just that we've added a small amount of pigment to one so that we can see the materials more clearly. So this is the prototype BU element that we've been manufacturing. Even within this element, you see that we need to address the question of a vertical layer, and we need to address the question of a horizontal layer. And that then takes us to this whole question of the feasibility of layered specimens. Key aspects are the fresh state compatibility of the materials that we use, the hardened state compatibility, the conditions under which we can even make these horizontal and vertical layers, and does the introduction of these interfaces lead to any detrimental consequences. For the purposes of this presentation, I'll focus primarily for the remainder of the talk on some of our work on fresh state compatibility. So within that sphere, what we found as two key parameters in looking at fresh state compatibility is the workability of the mix and the density. So by way of introduction, in the workability, we've defined anything from a stiff concrete to a flowable concrete. The kind of icons that we use is that we sort of have a cone shape for a stiff one, a sort of blob, flattened circle for the flowable, and then a blob for the in-between state of workability. Our density, when we've considered lightweight concrete mixes, we've achieved that primarily by using LITAG, so the density works out about 1,800 kilograms per cubic meter, and our normal weight concretes of the order of 2,400. And for the purpose of this talk, the normal weight I've colored pink and the lightweight are grayish. So let's consider, first of all, the question of two vertical layers. So by this, what I mean is that we have two columns of two different materials. They're segregated with a removable panel, and they're both cast separately, but still in the fresh state. We then remove the panel, and the question is, do the materials, broadly speaking, stay where they are, or do we have a movement of the materials relative to each other? And the driving parameters that we investigated were the workability, the difference in the density, and the geometry. And by that I mean how wide the specimen is, how tall the specimen is, for example. So what we did was we, in effect, cast a whole range of specimens using our different combinations of mixes. We would leave these to harden, and then we would slice through the center of the hardened section to see how much deviation from that center line we had. And that allowed us to define what we call the stability indicator, which is the extent of that deviation. We were then able to plot this in this following graph, whereby the vertical axis is the maximum horizontal displacement, so that's our stability indicator, and we defined what's called a stability coefficient, which is a function of the geometry, the workability, and also the actual density of the materials. So what that allowed us to do by considering that stability coefficient is define combinations of mixes that are likely to have stable behavior if they're placed side by side in these vertical columns. So that's allowed us to make progress with the vertical layers. We've also then looked at horizontal layers, and in this case we've deposited mix 1, and then again in the fresh state we will deposit mix 2. And again, there's a number of different outcomes. We may have that interface stays, broadly speaking, horizontally or roughly horizontally, or we may have significant deviations from the horizontal. So again, what we did, using primarily the driving parameters of density and workability, is we looked, and you see from this icon, at a number of different combinations of mixes. In the far upper left corner, you see that this would be the case where we had a stiff normal weight concrete, which was on top of a fluid lightweight concrete underneath. Then we in effect swap the mixes around, where we would have in effect a stiff lightweight concrete and a fluid normal weight concrete underneath. So in this case, we have these combinations. We looked at all the combinations in between and down to the far right-hand corner, where we would have, say, a fluid lightweight concrete on top of a stiff normal weight concrete. So we mapped across this space of combinations. We, as before, we cast these specimens and then we left them to harden, and then we would cut through them and we would look at what happened to the interface. Again, in this concrete, you see we've got both pinkish and gray colors defining the two different materials. We made some ideas about what indicators we'd use. In this case, we used a combination of the addition of the upper deviation plus the lower deviation to find what we call the maximum interface extent, which is a measure of how much there's been deviation from the mid-height. So in the subsequent plot, that's the measure that I will show. So this is a plot now of the yield stress of the bottom mix and the horizontal axis, and a yield stress of the top mix on the vertical axis. In this plot, the heavy mixes, when they're on top, are plotted in effect as the red, and when we have the lightweight on top, it's plotted as the black squares. And the size of the shape tells you the size of how much there's been of that interface deviation. And what that now allows us to do is start to look at what combinations give us significant deviation and which don't. So within this design space, what we've been able to do is define what we call compatible mixes, where there's relatively small deviations. We found there was also a region where the way that we deposited the materials made a difference to how much deviation we had, so we call those deposition influenced zone. And then we had in the lower left corner what we call the density driven zone. And that one's an interesting one because this is when both mixes were relatively fluid. And if we think that through, it turned out when we had the relatively heavy fluidish mix on top, we had a fairly large deviation. Where we had the lightweight fluid on top, we had much smaller deviations. So again, this now gives us a design space for fresh state compatibility. So what we're seeking to do overall with our tailored reinforced concrete infrastructure project is to reduce our CO2 emissions, redefine concrete as a high-value material, rethink our cement usage, and deliver enhanced performance. This project, as ever, there are many people involved, and I've named my collaborators on this slide, and I'm grateful to them for their contributions to the work in this presentation. This is also funded primarily by EPSLC, and we're very fortunate to have strong collaboration with Costain, Lang O'Rourke, and SOM in delivering this work as well. So thank you very much for your attention, and in due course, I'm happy to take any questions.